Hey everybody, here's the start of the video on 4-4. We're on page 210, numbers 1 to 21, every other odd, 29, 33, 53, and 57. So to start with, this is on concavity, curve, and curve sketching. And so the first ones are about analyzing functions from the graphs. It says identify the inflection points and the local maximums and minimums. The plural is maxima and minima. So basically we're going to do it, and we need to use the derivatives as well. Okay, so to start with, on this first one, we have y equal x cubed over 3 minus x squared over 2 minus 2x plus 1/3. And so what we do on that first is to get our derivative. If it helps you, you could write this as 1/3 x cubed minus 1/2 x squared minus 2x plus 1/3. That step is optional, but basically when we get y prime, you're going to do 3 times 1/3, which cancels. And so that's why you're going to end up with x squared for that. And then the next part, you're doing your minus 1/2 times your 2, so you get negative x. And then here you just make it negative 2. And then the derivative of 1/3 is 0. So this is your derivative. What they want you to do next is to factor that out like reverse FOIL. And so you know it have to be x and x because you end up with x squared. First times first is x squared. And then you know you have a 2, and that means you're going to have a 1 and a 2. And then we have to figure out which one's positive and which is negative. So based on the middle term being negative, the 2 has to be negative and the 1 has to be positive. So that's what you get for y prime. Then we need to do y double prime, and then that would be 2x minus 1. And the derivative of negative 2 would be 0. The next step on this is they factored out a 2. It's a little weird to me when I looked at it, but then once you see what they did, it kind of makes sense. So if you factor out a 2 from here, you get 2 times x, it's 2x, and then over here you'd have to say minus 1/2. Because 2 times negative 1/2 gives you negative 1. The reason is because they're going to use factor out a 2 to use 1/2 on an interval. And we'll get to the intervals in a few minutes, but to start with, we're going to use negative 1 and 2 on these intervals for f prime. I'm sorry, y prime, same thing. And this is an interval for y double prime. So basically these numbers are negative 2. Sorry, I've just put negative 1. Yeah, negative 1, 1/2, and 2 are the points that are interesting. And so when we look at the graph, the negative 1 gives you the maximum. And we can do this on the calculator also. We have x cubed over 3, minus x squared over 2 minus 2x plus 1/3. So that's the graph which was in the book, and we need to do maximum. So analyze and then maximum between here and here. The lower bound, click and click. That gives you the -1, 1.5. So -1, 1.5 is the local max. And now we're going to do the minimum. Two comma -3 is the local min. So what that tells you is the graph is rising. The graph is rising on -infinity to -1 and from 2 to infinity. Because those are both places where it's going up. So basically from -infinity to where the x value is -1, and then from this x value to infinity. And then the decreasing would be between. So then you have falling on -1, 2. So that's about the rising and falling. The next part is about the concave up and concave down. So the concave up would be from 1/2 to infinity. So concave up means it's kind of like a parabola, and you can't choose 0 because it's still going down, but halfway between it starts being concave up. And so if we knew we had to split the difference, that's how you can get it. That's one way to do it. And then the concave down is from -infinity to 1/2. Okay, so now I'm going to show you the book way to get this. Okay, so as I was saying, here's how the book does it. This is an example with a different function, and it wants you to identify the extrema and then say where it's increasing and decreasing, then concave up and down to graph it and plot points. So I believe this would be the best example from the book to refer to. So you can see it here. And so the first thing they're doing is graphing it and saying it's continuous because the derivative exists. And what they did is they had x to the fourth, which turns into 4x cubed. So basically you bring your 4 in front and decrease the power. Then you take your negative 4 times 3 and get negative 12 and decrease the power. So that's your derivative. And the domain of the original was all real numbers because all polynomials have all real numbers. And then the derivative is also a polynomial, which is also all real numbers. And so the critical points occur only at the zeros or x-intercepts. And so they had this function and they factored out the x squared and the 4 and they got this. And so 0 and 3 would be the values. And then from there they saw decreasing, decreasing, and increasing like we did in the other section. So that's the first step. The next step is they said use the first derivative test, and there was no extreme at 0, and they had a local min at 3. Then they used their table to see where it's decreasing at those 2 spots and increasing at that spot. The next step they did was they took their derivative of the derivative. So the second derivative was 12x squared minus 24x, and so they factor out the 12x. And so they end up with 0 and 2 for your boundaries. And so then on the left side they saw it was up, on the middle it was down, and on the right side it was up. So that's basically like what we're doing as well. And then this says summarizing, we get decreasing and up, decreasing and down, decreasing and up, and increasing and up. So it's not always with decreasing with down. You had to do your other test. See what the sign of f double prime is to the left of it. So we're going to have to check different values. Like you could check -1, -5, -10, or whatever. And then on this one you could check 1, and on this one you could check 3, 5, 10, or whatever that's bigger than 2. And so this was the information they got. So from that, they saw decreasing with up looks like this. So the graph is decreasing, but it's, concave up. And then this one is decreasing but concave down. And so as they're piecing it together, they just do that. Then the next part was decreasing with up and then increasing with up. So that's why it just connected like that. Now I know in most of your cases you just like to graph it, but they're using these information points and intervals in order to tell you the general shape. Okay, so now going back to ours, to make sense of this, we had our original function, which was in the book. That was the original y. And then for f2, this is our derivative function, which is x squared minus x minus 2. So that's the red one, basically. And that gives you your x-intercepts, which are -1 and 2. And so that's how we know what intervals to use. And then our second derivative is 2x minus 1. If you don't want to factor out the 2, that's fine. I mean, you just need to know that you get 1/2 from your x value. Well, Okay, so your x value is -1, but they did 2 times -1/2 in order to get the -1. Okay, so then they tested points. And from -1 to 1.5, from -1 to 1.5 was a maximum, and then to -3 was a minimum. Okay, so then it's rising from -infinity to -1. So talking about the original graph, the original graph is rising from -infinity to -1, talking about the x values, and then also from 2 to infinity, and it's falling in between. So that part is pretty much self-explanatory. And then on the concave up and concave down, that's where you have to use your formulas and your graph. So the definition that I'm applying here is, well, we need this part, this part, this part, as well as your derivatives and functions. So I just did a box around whatever you need to write. Your original, your derivatives, your minimums and maximums, and then the description of the rising, falling, and the concave up and down. So the rule that we're using is if f double prime is greater than 0 on I, it's concave up, and if f double prime is less than 0 on I, it's concave down. So the points they used were the -1 and the 2. Okay, so we knew that 1/2 was what we were going to talk about for the y double prime. And so when we have x less than 1/2, I decided to try 0. If you would rather try a different value to the left of 1/2, you could have. But 0 was just an easy number. And I'm using f double prime. So that means the 2x minus 1. So what I did is I did 2 times 0 minus 1. 0 minus 1 is -1. Since it's negative, then it's going to be down. And so that's how you can get this part. Down from -infinity to 1/2. And then on this side, if 1/2 is your left bound, then you could try 1, 5, 10, whatever. I tried 1, and so 2 times 1 is 2, 2 minus 1 is 1. It's positive, so it's up. And so that's how we got up with 1/2 comma infinity. So this is the work for this. That helps you understand how to get your answer. Earlier we talked about the maximum and minimum, and so the way they describe that is 1.5 is the max at -1. But at the MathXL, they might want a fraction, so you could say 3/2 is the max at -1. So just look at whatever form it wants. And then the other one, -3 is the minimum at 2. The other point that they're interested in is when you have your 1/2. And let's just go to the table to make it easy on this. Control T. Let's just choose this to be independent to ask. And I'm going to put 0.5. So when we do that on the original, we get -0.75. So again, on your original, okay, on the original, you also have a point of inflection at x equal 1/2. That value was from the second derivative. And when you plug it in, it was 0.5 comma -0.75, which was 1/2 comma -3/4. So make sure you have this part also. And that's number 1.